it correctly. Second inverter, this one second, this is first, second and third. This VIL is the maximum allowable voltage at the input of the second inverter, which is low enough to ensure a logic 1 output. See here, maybe VOL, but normally VOL, we have seen that should be, in case of CMOS circuit, equals to VDD only, but it may be a little low than that also. Maybe say in a VDD equals to 1 volt system, I am assuming 0.8 volt, and the VTN and VTP, I'm assuming 4 volt, VTP equals to minus 0.4 volt. Okay, I'm assuming this voltage values, and hence the VOL 0.8 volt can be very well considered as high output. And if it is applied to second inverter input, second inverter's input, then obviously there will be no problem. Okay, but if 0.8 volt you are applying here as high, then no problem. It may give zero output. VOH ideally should be 0, but it may be a little more also. VOH ideally ground or 0, but it may be its value, maybe we can assume that it is a 0.2 volt. Let me assume it. That also can be thought of as low. But so, for example, this output VOH applied without any change by the interconnect, no problem, we may get the correct output from the second inverter. But if this interconnect adds some noise due to capacitive or inductive coupling, and if it is in the negative direction, say 0.3 volt, negative spike is coming here, then what will happen? So 0.8 minus 0.3 is going to be 0.5 volt. So can you think of this one as high? What is the situation of this P MOSFET in this and MOSFET in this second inverter? The P MOSFET in this case, let us consider the P MOSFET in this case, second inverter case, will be what? If your V in should be actually 1 volt, but due to noise and other reasons it is 0.5 volt. What will the state of P MOSFET? And what will the state of N MOSFET? So this inputs for the second inverter may be not interpreted correctly and wrong output may be given. So these interconnects are issues. These interconnects are a lot of problems in interconnect, especially nowadays, because earlier it was thicker and wider. Now due to scaling of the device, or technology scaling rather, not only device dimensions are reduced, but interconnects are also, its width and thickness has been reduced. So it is going to offer more resistance also. So a resistive drop will be there. Plus nearby another line, interconnect line will be going. That may carry some signals like clock. That signal, clock signal, will be affecting this signal. So it is going to cause a huge problem. So margin, noise margin should be high, so that if noise occurs, then also the um, gates here, inverter, maybe other gates can give desired output, right? So next topic in our second module is nothing but interconnect. Whole module is on interconnect, and hence we have to study talking about these two. Assuming that the second inverter produces an output voltage level of VOH, here VOH is being produced. As in the previous case, this output signal will be disturbed because of the noise interference, and the voltage level at the input of third inverter here will be different from VOH. If the input voltage of the third inverter is larger than VOH, this signal will be interpreted correctly as logic 1. If the signal, I'm here in the same good direction or appropriate desired direction, you can say noise comes, then no problem. VOH say 0.8 volt. If it is in, inducing a voltage here in positive spike or positive direction, then there is no problem. But if it is in opposite direction, then there will be a problem. If due to noise VOH is less than VIH, then third inverter may not interpret correctly. Thus, VIH is the minimum allowable voltage at the input of the third inverter, which is high enough to ensure a logic 0 output. So, calculation of NML and NMH are this. VIL minus VOL is the low noise margin, and VOH minus VIH is the high noise margin. And remember that if noise margin is higher is better, the circuit will be more immune to any noise. In this diagram, it is more clearly given. This, you say that this is the output profile. Output profile of, say, first inverter. In earlier we have discussed, and this is the input profile. We have already shown some diagram in the previous lecture. It was right side. Input profile was right side. Input profile of second inverter. Here you can very well understand what is the definition of NML. NML is here VIL minus VOH. This I was assuming that it is say 0.2 volt. This you take VIL. Let us take it is at as point say 3 volt. So NML will be means the first inverter output should be considered as low if it is 0 to 0.2 volt, for example. Okay, and the second inverter will consider its input as low if it is coming from some first inverter up to 0.3 volt VIL. Okay, so difference between these two is NML. Here the output profile, say I'm considering this one as 0.8 volt. VO equals to VDD is the ideal value, but it may be below VDD, say up to 0.8 volt. We can consider that its output voltage up to 0.8 volt is considered to be high. And in the input profile side, if you see the second inverter input If it is say up to zero point 0.7 volt or so, let me consider 0.7 volt. If some input is coming from this side and it is 0.7 volt, then also it will be considering as high input, VIH, input high. So noise margin here will be this 0.8 volt minus 0.7 volt. Okay. So this is the concept of noise margin, but how to be calculated mathematically is here. We know that VIL, these four things, VIL we should know, VIH we should know. These two things we are supposed to know. And we know that VM, sometimes it is denoted by VTH, or sometimes it is denoted by VINV, inverter switching threshold voltage. Variously, it is denoted by different literature, different book. So this is also, we know that it is ideally or well-designed inverter should give VD by 2 at the middle of the supply voltage. Okay, so to calculate mathematically the noise margin, we should have the knowledge of VIL and VIH. If we consider VIL equals to ground in a CMOS case, in CMOS case, VOL can be considered as 0, equals to 0, and VOH can be considered as, say, VD. For simplicity, we can assume that CMOS normally in other circuit like pseudo NMOS, pseudo NMOS, pseudo NMOS circuit VOL will never be 0. Pseudo NMOS circuit, can you remember? We have discussed once, Rajwal or somebody, Ashwardhan. Yes.
PMOS is connected to ground and
Yes, something like this. PMOS is here permanently grounded, so it is always on. Here is the input. Okay, is output. So since PMOS is permanently grounded, it is always on. If you apply 1 here, so this is on and it is going to pull down. The NMOS is going to pull down the Vout node, output node, towards 0. While doing so, it has to fight against the on PMOS. So its output will never be, its output is not going to be proper 0. Okay. It is going to be somewhat above 0. Okay. That depends on how much VOH is how much. It is 0.1 volt, or it is 0.2 volt, or it is 0.3 volt. That will depend on the strength ratio, or simply you can say that if length is same, then width of N MOSFET and P MOSFET. Strength of a N MOSFET or P MOSFET can be increased by width of the MOSFET, taking L same. Okay. So in this case, you see that never it will be 0. But in case of CMOS inverter, this kind of inverter, it will be 0. So we can assume for CMOS gates that VOH is VDD and VOL is ground. So how to calculate the noise margins, that we are going to see. We are going to mathematically see what is VIL, then VIS, and then here, see, VIL occurs where? Let me show another diagram which we have already shown, but you may not be remembering. See, VIL occurs when the gain dV out by dV in equals to -1. This is the input voltage. D in is that input voltage D in VIL is that input voltage at which the gain is -1, and VIH is that input voltage at which again gain is -1. This first one, that is VIL, is in region B and VIH is in region D. That must you remember. This diagram will be useful to understand. So in this region, can you say in this B region B, what is the status of MOSFETs, N MOSFET and P MOSFET? They are in which region? We have already shown, but you must be able to say. Hmm? What is the status of NMOS? Somebody say NMOS is in which region?
Linear.
NMOS is linear, you say. Okay, somebody, any other opinion? PMOS? We're talking about B, region B. See, we have
Sir,
thoroughly discussed.
sub-threshold region.
Which one?
Sub-threshold regions.
PMOS. You're talking about PMOS.
No, sir, NMOS.
NMOS subthreshold region. PMOS? Tell.
In cutoff.
PMOS is cut off. PMOS is cut off. This is your answer. Okay, somebody is telling cut off, and others are not telling anything. And NMOS, somebody is telling linear, somebody is telling subthreshold. This is the condition. Okay, and this lecture we have discussed just in the previous lecture. Okay, this thing we have discussed in the previous lecture, and I said that you study. See, region B is here. You are not using your intuition also, not studying also, not doing anything. There also you have discussed. See, the discussions are here, but it doesn't matter you whether you understand or not, doesn't matter. So it is pointless to go into that detail. For the second module, I am going to give you the previous lecture videos. You study it. I'll cut short only in 1 or 2 lectures. 10 lectures I took in the previous year. I'll be uploading those videos. You study. If you have doubt in any of the video, then you will ask me. Okay. I'll cover within 1 or 2 lectures. Just I'll show the slides and finish it up. There is no point. There is no point. You are not paying any attention. I have taken very thoroughly regarding region of MOSFETs. See, we know that V in equals to VIL occurs in the region B when NMOS operates in saturation region and PMOS operates in linear region. Equating their currents, because currents flowing through the NMOS and PMOS is going to be same. So equating these current equations. See, this is for N MOSFET. Obviously, it is saturation region equation. Yes or no? That also you don't know. No idea. This equation is in which region's equation it is? Hmm?
Saturation region.
Saturation region.
Saturation region.
This is VGS. VG. This is VG. V in is VGS. And VGS minus VTN whole square. V is your mu n C ox W by L, which is called gain factor also. That is beta. Instead of writing this, beta is written. Beta is written. Here you see, look at, this is the linear region equation of P MOSFET. This is VG. Okay, this is VS. Source voltage is drain voltage is sorry, source voltage is VDD. So VG minus VS. This is VGS actually minus VTP into, it is what? VO minus VDD. What is this one? Is it not VDS? The drain voltage of the P MOSFET is the output voltage or not? Okay, inverter. So this is drain voltage. P MOSFET will be what? Beta P. Or I used to write in this way, mu P C ox W by L into what? VGS minus VT P into VDS minus VDS square by 2. This was the equation. Can you now relate this equation?
Yes.
This is your beta. This is your beta P. This part. Okay. VGS, this VG S, VG nothing but input voltage. VG minus VS. This is VGS. VG in input voltage. Should I draw here inverter, and then only you'll understand. V in. This is source, drain, source. V in is what? V in is with respect to, this is ground only, 0. So V, this is the voltage between this is what? This point to this point. Is it not V in? That is VG and VS. Okay, yes, VS is nothing but VDD. So is it understood? This is your VGS. Yes. This is VGS minus VTP, and this is what? It should be VDS. This is VD. This is VD and VS. Okay, VS is nothing but VDD. VD is nothing but VO. This is output voltage, na? VO.
Yes. Yes, sir.
VO minus VDD is nothing but VDS. Yes. And minus same thing square. And it was half here, but you have put here 2 and here beta by 2, beta P by 2. So you have. Yes. Are you getting this thing? Now it is understandable. The equations are understandable. Yes, sir. Okay, now you manipulate it mathematically. I mean, you are doing nothing but opening up, I mean, expanding the equations. And now you are differentiating this equation with respect to V in. And you are going to get this one. Look at, is it possible to get it or not? This, if you differentiate with respect to V in. Are you getting this one? Yes or no?
Yes, sir. Yes, sir.
Then, if you do here, what do you get? 2 beta P V in, then is it coming? This thing? Simple derivation. differentiation, sorry, with respect to V in. Is it happening or not? Hmm? For this one, you consider first, then you consider this part, and then last one. It is elaborately expanded so that you can understand. Mathematics, you have done a lot in the first and second semester. Is it understandable or not, this differentiation?
Yes, sir.
Yes. Yes, sir.
Understood? If you are understanding, then substitute V in equals to VIL and dVo by dV in equals to -1. This is the region B. We are talking about region B because we are talking about VIL. Understood? So VIL is that input voltage V in at which dVo by dV in equals to -1. So putting this and manipulating it, we get this equation. Now dividing numerator and denominator by beta p and putting beta n by beta p equals to kr, we get VIL equals to this. This is the ultimate expression. BTP plus 2VO minus VD plus KRVT n by KR plus 1. We can get from this current equation, we can get this VI, value of VI. Take this snapshot and check each steps. If anywhere any mistake is there, you can tell me later on. These all steps not given in the book. You can see the not all, only results will be given. Maybe this equation will be given, this equation will be given briefly. I have expanded so that you can understand easily. So VIL value you have got in this form, equation 5.61. And then we know that D in equals to VIH occurs in the region D when n MOSFET operates in linear region and PMOS operates in the saturation region. Equating their currents will again, now in MOSFET's equation linear region and PMOSFETs in saturation region. See, is it not the equation in saturation? This is what? VGS minus BTP whole square and beta P by 2. Yes, understood? That's well. PMOSFET in saturation. This is a linear region equation. Same way, linear region equation. Equating this and manipulating, you get this one. Then we do the differentiation with respect to V in, and later on you put V in equals to VIH and dVo by dV in equals to -1. And manipulating, you get this expression, and dividing numerator and denominator by beta p, we get this beta n by beta p equals to kr. Putting that value of kr in this expression, we get Vi's value as this Vd plus Vtp plus kr into 2 Vo plus Vtn by 1 plus kr. So two important values we have got, input values, input voltages, that is VIH and VIL. Now, the inverter threshold voltage is also important for us, VM. It is sometimes denoted by VH, VTH, or VI in. It occurs in the C region when both transistors are in saturation region. So, equating their current equations, this is the N MOSFET saturation current equation, this is the MOSFET's saturation current equation. And now manipulating it, we get VM equals to this. So mathematically, we can obtain the value of VM, switching threshold of the inverter. Threshold voltage of MOSFET is different from the switching threshold of the inverter. Remember that. Shashank, understood? Any doubt in this
Yes,
clarification?
sir. I understood, sir.
Understood? Any uh, difficulty in understanding? Say here we are this from this step and this step. Are you getting? I put a note here, side note, that will help you to understand. Look at and say, understanding or not.
Yes, sir.
But here, why the minus sign is understanding?
Where, sir?
Here, in the denominator, we have B in minus VD minus VDP whole square, right? And we are taking the root.
Yes, sir.
Root of this, square root of this equation. We are putting minus 1. Why?
Sir, after taking root, it can be the plus or minus, sir.
It is
Plus
a
or
negative
minus.
quantity. So
So this internal thing is a negative quantity. Do you understand this? Why negative quantity? So to take the positive root, you have put a minus sign here. This is understood or not? First of all, before that, you have to understand that this is a negative quantity. Inside the parenthesis, this is a negative quantity. Is it negative quantity? Take some example value. Say VDD equals to 2.5 volt. Okay. And then V in is what? Tell me. And VTP equals to say minus 0.4 volt. Tell me what is V in? Hmm?
1.25.
1.2. Very good. 1.25 is the V in. Now, is it not a negative quantity inside the parenthesis? 1.25 minus 2.5 minus 0.4 volt. So it is what? So 1. What is that? 65 minus 2.25. Sorry, 2.5. Is it not? This minus plus 0.4 volt plus 1.25 volt. So it is 1.65.
0.85.
So it is minus
0.85.
0.885. Anyway, whatever is. So this is the negative quantity inside the parenthesis, and we want to take a positive root. So we have put a negative sign. This is the catch of this. Otherwise, everything is simple. So you are getting Bm as this expression. Btn plus within parenthesis VDD plus BTP square root of beta P by beta n. In the denominator, we have within parenthesis 1 plus square root of beta P by beta n. So expression of Pm you got. If you know the current equations and know the regions of operation of the MOSFETs, equating the current equation, you can do it. We know that in region C, Bm occurs, or B in equals to B out equals to Bm occurs in the region C, which is indicating or telling that both the MOSFETs are in saturation region. And taking the saturation energy equation, equating them, we get this value. Anyway, there is a problem, numericals. Consider a CMOS inverter circuit with the following parameters. VD equals to 3.5 to 3.3 volt, VTN equals to 0.6 volt, VTP equals to minus 0.7 volt, beta N equals to 200 microampere per volt square, beta P equals to 80 microampere per volt square. Calculate the noise margins of the circuit. Means you have to find out NM, L, and NM, H. Okay. So now you can do that if you put the values. It is a CMOS circuit mentioned here. So you can consider VOL equals to ground, VOH equals to VDD. That means it is 3.3 volt. This much you can assume because it has been mentioned it is a static CMOS inverter. Okay. So with this you can do it. So VIL we have to find out first, then VIH we have to find out. Then only you can obtain the noise margins because we know using this equation already we have derived, and hence you will get at the end this value 0.57 VO minus 0.71. VIL equals to 0.57 VO minus 0.71. And putting the value of VIL in the V in the equation 5.59. This is the equation 5.59. I have brought it from the previous slides, and putting these values of VIL, we can get this expression, and this expression reduces to this zero point 0.6 is VO square plus 0.05 VO minus 6.65 equals to 0. The one root of this quadratic equation is physically correct solution for VO when VO greater than 0 means positive. Okay. And VO, hence VO will be 3.14 volt output voltage. Okay. From this value, we can calculate VIL. Okay, because previously we have seen VIL expressed in terms of VO. So putting this value of VO, we get VIL equals to 1.08 volt. Understood? One value is obtained. Now, second value we have to find out VIH. To calculate VIH in terms of output voltage VO, we use equation 5.67. This is nothing but this equation which we have already derived. Okay, so put these values, given values, and get the equation in this form in terms of VO. Now putting this value of VIH in equation 5.64, we get this expression. After simplification, we come up to this point. And only one root of this quadratic equation is physically correct solution for VO at this operating point, that is when V equals to VIH, VO equals to 0.27 volt. So from this value, we can calculate VIH as 1.55 volt. We can now calculate the noise margin. NML equals to VIL minus VOL, and VOL equals to 0 for CMOS circuit. So it is put 0. Okay. And we get the value of NML as 1.08 volt, and NMH equals to VOH minus VIH. Hence, it is 3.3. This is nothing but VDD. Okay. CMOS circuit VOH can be considered as VDD. So that is written 3.3 volt minus VIH equals to 1.55, which is here. So you get NMH equals to 1.75 volt. Is it clear? Now we have to study dynamic behavior of CMOS. In this, we'll have to estimate or understand the various parameters of CL, and we have already understood that there are various components, at least 3 components, you know.
Interconnect capacitance, drain diffusion capacitance, and COX.
COX of the fan outlet. Okay.
Yes, sir.
You are Karthik?
Yes, sir.
Okay. Arts Tripathi, are you there? Arts Tripathi is not there. Himanshu Shogra, Prabhat, not there. Okay. So this implies that getting CL as small as possible is better for realizing high performance circuits. We know that because to get the output, what is done actually? It is the CL is charged or discharged. The charging and discharging time will depend on the value of the CL. So its value low means quickly it can be charged and quickly it can be discharged. So hence it is better to first study the major components of the load capacitance before starting an in-depth analysis of TP of a gate. TP means propagation delay. Okay, propagation delay. Propagation delay is denoted by TP here. So manual analysis is very difficult, but something we can understand from here in the diagram. Hence it is assumed that all capacitances are lumped together into one single capacitor. See, many times, capacitors are there which are not grounded, or one end is not connected to ground. So it is called floating capacitance. This one are floating capacitances. So you have to use the Miller theorem, then only you can get it. So you can simplify with lump CL. Okay, it is a considerable simplification of the actual situation, even in the case of simple inverter. Okay, if you are just lumping all the capacitors in one value, say CL, then it is quite simplification, which may not be so accurate. This is only grounded cap. Otherwise, these three capacitors you are seeing, they are all floating. In this figure shows the schematic of a cascaded inverter. Here it includes all the capacitances, including the transient response of node V out, influencing the transient response of it. So all are having impact on, output transient, how fast it is happening or slow is happening. It is initially assumed that input V in is driven by an ideal voltage source with zero rise time or fall time. Means V in is considered to be square wave kind of output input here, without any rise time like this or fall time like this. It is assumed that it is like this, but in real circuit it will not be. Accounting only for capacitance is connected to the output node CL breaks down into following components. One component is gate drain capacitance CGD 12. Okay, CGD 12 is this one between gate and drain. We know that we have drawn earlier MOSFET and capacitance around that we have drawn CGD, CGS, etc. we have drawn. So gate to drain capacitance. It is of both the MOSFETs. It is drain of this one as well as drain of this one also in MOSFET also. So M1 and M2 are either in cutoff or in saturation mode during the first half out up to 50% point of the output transient. Which half it is talking about? Can anybody say? It is written.
Switching threshold.
No, it is written that M1 and M2 are either in cutoff or in saturation mode. In the saturation mode during the first half of up to 50% point. during the first half of the output transient. When output is making a transition, okay, maybe from high to low or low to high. Suppose low to output here D output making a transition from high to low. Or low to high.
Then is it switching threshold voltage?
So
30%.
50% up to 50% point up to BM. Yes, if it is designed that way, that BM is middle of the threshold voltage. Sorry, middle of the VDD, then BM. So you'll see that when it is falling from high to low, then n MOSFET is in which region? Output is falling from high to low. Is it not in saturation region?
NMOS is initially
N MOSFET. NMOS initially cut off.
Then saturation, sir.
Then it is saturation region. So most of the time, I mean, when B out is high, your N MOSFET is off. After that, when it is, I mean, output node is falling from cutoff to it will enter into linear region, isn't it? Then saturation. During the C region, it is saturation region. And then when it is rising, initially it was what? On? No. Output is rising means it was 0, means it was on. From on state, it is in MOSFET was on in this position or not? When output, this is B out, remember. NMOS, when out is 0, NMOS was on, and then it is entering to which region? Initially, when BM, then it is B out equals to BM, then it is in saturation region. But before that, what the region is? It is linear or not? See, BM means, say, I'm considering BDD equals to 1 volt. So BM means 0.1.
Linear region.
Linear region. How linear region? We know that VTS greater than equals to VGS minus VT is saturation condition. Okay. So VTS here is 0.3 volt. Okay. VDS means output voltage only. Is it greater than equals to VGS minus VT? VGS is 1 minus 0.4 volt. So this is not true. It is false. So it is in linear region or not?
Yes, sir.
So after that, it is entering into the saturation when your region C or VM is reached. Anyway, so the statement written here, M1 and M2 are either in cutoff or in the saturation mode during the first half up to 50% point of the output transient. Under these circumstances, the only contributions to CZD 1, 2 are overlap capacitance. See, overlap capacitance we have discussed, understood? Yes or no?
Yes, sir.
So these two transistors overlap capacitance will be here, there will be overlap, and here there will be overlap. Those overlap capacitors will be there. overlap with gate and drain. Actually, gate and drain. CGD we are talking about. The channel capacitance of the MOS transistor does not play a role here as it is located either completely between gate and bulk cutoff region or gate and source saturation region. In saturation region, we have seen that what are the capacitance in saturation region? CGS equals to 2/3 of say COX into WL, something like that. Something like that. Total out of the total capacitance, it is 2/3. And CGD, what is the value of CGD?
0.
It is 0. So if CGS is there, CGD is not there. So its effect is not there. We're talking about the drain, CGD. Its effect is not there. We are not bothering about the CGS because CGS is not involved in load capacitance. It is involved with the drain capacitance only. This you understood. This is understood or not? Gate to source capacitance is not our concern. Gate to source capacitance here, this one is not our concern because this capacitance is not connected to the output node. We are concerned about the CL. That has to be charged and discharged. Is it understood? If self-aligned CMOS process is used for fabrication, then the effect of CGD 1-2 can be neglected because in that case overlap will not be there. Okay, so CGD 1-2 can be, if you want, can be overlooked, can be avoided because if it is in saturation region, there is no effect of that capacitance CGD. It is 0. Yes, if you consider the overlap part, okay, but if it is what is that? Self-aligned process, then overlap will not be there. So effect of CGD is nullified. You can ignore it. If otherwise, if it is not self-aligned, then you have to take care of. And in that case, double value will be going there. Why? We'll discuss here. Gate to drain capacitance CGD to 1-2. We have to further understand a little bit. If we don't ignore that overlap, I mean, if it is not self-aligned, then how to take care? The long capacitor model now requires that this floating gate drain capacitor be replaced by capacitance to ground. Instead of this, we have to write a capacitance, use a capacitance which is connected between output node and the ground. For that, you have to apply the Miller effect. Okay. Okay. During a low high or high low transition, the terminals of the gate drain capacitor are moving in opposite direction. Okay. If this is increasing, the other side will be decreasing. That happens? Yes or no? In capacitance, what happens? If positive charges are deposited here, negative charges will be there or not? What is the capacitor?
Yes, sir.
So double, I mean, voltage or charge across CGD1. Voltage due to this charge across CGD1 is delta V. So delta V you are changing at the input. Then in opposite direction delta V will be there. So basically delta V minus delta V, 2 delta V will be there. So once you replace this capacitance with a grounded capacitance, this is a floating capacitance. If you replace with grounded capacitance, then you have to write double of that value, 2 into CGD1. Understood? Why it is 2? Because of this. This is what if you consider. Consider means it is not overlap. I mean, self-aligned process, the overlap will be there. Then you can consider it, and if you are considering, then CGD should be replaced with a grounded CGD multiplied by 2 in this case. To present an ideal load to the output node, the capacitance to ground must have a value that is twice as large as the floating capacitance, floating CGD1. Is it understood, Prajwal?
Yes, sir.
Gate to
Sir,
drain capacitance.
excuse me,
Yes.
sir.
Hmm.
Sir, we have a class now, sir.
Okay. We'll end here. We use the following equation for the gate to drain capacitance. CGD equals to 2 CGDO into W, where CGDO is the overlap capacitance per unit width as used in the SPICE model. For an in-depth discussion, you might have come across Miller in analog circuits. I think it was discussed, so you can refer back. Anyway, this was good enough to understand. The diffusion capacitance CDB1 and CDB2 will be discussed in the next class. Be prepared for the exam and quiz one by first this Saturday, Sunday or Saturday. Okay then.